artificial intelligence. It's really not just science fiction anymore, is it? It's kind of woven into our daily lives now.
Oh, absolutely. It's everywhere. Your digital assistant, how you shop online, even, those generative AI tools like ChatGPT that so many people are using.
Right, exactly. It feels incredibly fast, almost seamless. How integral it's become. Genuinely revolutionary.
It is revolutionary,
Right.
definitely. But that speed, that innovation, well, it comes with a hidden environmental cost, a pretty heavy one.
Okay.
And our sources today really dig into that. They explore this uh, massive growing footprint, not just the software, but the real world demands on energy, water, hardware.
Yeah, and that's our mission today, right? To try and quantify that demand because the scale we're talking about here,
Right.
well, it's pretty staggering. We're not talking small changes.
Not at all.
Yeah.
Let's start with electricity. Just think about this. In 2023, data centers were already pulling 4.4% of all electricity in the U.S.
4.4%, that's huge already.
It is enough to power whole states. But the projections, they suggest that number could triple by 2028.
Triple.
And AI is the main driver behind that surge.
Triple is.
Yeah.
Yeah, hard to even picture. And if you look globally, the strain on power grids sounds almost, well, unimaginable.
Exactly. Some estimates are suggesting data centers could account for maybe 20% of the entire world's electricity use by 2030, maybe 2035.
20%. That's not just like needing a few more power plants. That fundamentally changes global energy demand.
It really does. And you can see this growth directly in the AI-specific hardware. The energy used just for those servers, it jumped from under 2 terawatt hours back in 2017 to over 40 terawatt hours in 2023.
40. That's a massive leap.
It's an explosion. And it's tied directly to how these big AI models, these large language models or LLMs, are actually built and then how we use them every day.
Okay, let's get into that. The mechanics. Researchers often talk about two main phases, training the model and then inference. Why is the training part so incredibly power hungry?
Well, training involves this incredibly complex process of adjusting billions, sometimes trillions, of parameters in the model. It's like trying to teach it everything all at once by crunching massive data sets repeatedly.
Okay.
This needs serious computing power. High-performance computing, HPC, we're talking thousands of specialized chips, GPUs and TPUs, running flat out nonstop for weeks or even months.
Just constantly running.
Constantly. So that initial training phase, it's one of the most resource-intensive computing tasks humans have ever really undertaken.
And we have a number for that, right, for GPT-4. That really puts it in perspective.
Yeah, the estimates for training GPT-4 alone are around 50 gigawatt hours of energy
50 gigawatt hours.
and costing over $100 million just for the training run.
And to make that concrete for you listening, that amount of energy could power, what, the whole San Francisco metro area for about 3 days?
That's the estimate, yeah. Just for that one initial training session.
Okay, so that's the huge one-time upfront cost. But you said the energy demand shifts after that.
It shifts dramatically.
Yeah.
And this is where it really impacts daily use and the overall footprint. After training, the vast majority of the energy, like 80 to 90% according to research, goes into inference.
Inference. That's when we actually use it, right? When I type a question into ChatGPT or ask an AI to generate an image?
Exactly. It's you, the user, making a request.
Yeah.
And because millions, maybe billions of these requests are happening all the time now, that's where the bulk of the continuous energy drain comes from.
So all those seemingly small interactions, summarize this, write that, create this picture, they add up massively.
They really do. It's pretty striking that a single query to something like ChatGPT can use about 5 times more electricity than just doing a full Google search.
5 times more, just for one question.
And what's really interesting, and maybe a bit concerning, is how much that energy use can swing depending on the model.
How so?
Well, it depends heavily on the size of the model you're querying and how complex the task is. Our sources looked at open source models like Meta's Llama series to try and get a handle on this variance.
Okay, yeah, let's look at that data. That sounds like a key point.
Right. So take a smaller text model like Llama 3.1 8B. The 8B means 8 billion parameters. A single response from that might use around 114 joules of energy.
Joules are tiny, right?
Yeah.
114. How can we picture that?
Researchers use comparisons. So 114 joules is like riding an e-bike for maybe 6 feet or running your microwave for just a fraction of a second, like a tenth of a second. Sounds tiny.
Okay, almost nothing. Seems efficient.
Seems efficient. Now, compare that to a much bigger model, Llama 3.1405B. That's over 50 times larger in terms of parameters.
Okay.
A single response from that model jumps to around 6,706 joules.
Whoa, okay. From 114 to over 6,700, that's a huge leap.
Yeah.
What's the microwave comparison for that?
That's like running your standard microwave for about 8 full seconds.
8 seconds versus a tenth of a second, just for a similar text output.
Potentially, yeah. The researchers use microwaves because they're a familiar high-power appliance. It gives you a more visceral feel for the difference in energy consumption.
So why? Why use the big, energy-hungry model if a smaller one could do the job for many simple queries? Why the massive jump in energy use?
Well, the thinking, which has some backing, is that bigger models are generally smarter, more versatile, less likely to make errors or hallucinate. They can handle a wider range of tasks.
So capability trumps efficiency.
Often, yes. A platform might default to the bigger, more capable model, even if your specific query didn't really need it. So you end up paying the higher energy cost for every single request, basically. Scale is kind of the enemy of efficiency here.
And we've only talked about text so far. What about generating images or even video?
Yeah. That's where the numbers just go into another league entirely.
Yeah.
Generating, say, a 5-second video with an open source model like CogVideoX.
Okay.
That single task takes about 3.4 million joules.
Million. Wow.
Yeah, that's over 700 times the energy needed to generate a pretty high-quality static image. Or, sticking with a microwave comparison,
Let me guess, it's longer than 8 seconds.
it's like running your microwave continuously for over an hour, just for one 5-second video clip.
Okay, that's genuinely shocking. An hour of microwave power for 5 seconds of video.
Yeah.
It really highlights how the type of AI task drastically changes the impact.
Absolutely. It's not just if you use AI, but what you're asking it to do. And this enormous energy use leads directly to another major, often overlooked issue:
Which is?
water. All those chips working so hard generate a phenomenal amount of heat.
Right, they need cooling, massive cooling systems.
Exactly. And modern data centers rely heavily on water for that cooling. We're talking vast amounts of fresh water.
Yeah.
The estimate is around 2 liters of water for every single kilowatt hour of energy the data center consumes.
2 liters per kilowatt hour, and is that water recycled?
Often no. It's what's called consumptive use. A lot of it evaporates in cooling towers or becomes contaminated with chemicals and can't just be put back into the local water system.
So it's competing directly with local water needs. Drinking water, agriculture.
Directly. And we're seeing the impact in corporate water usage figures. Google's data center water use jumped 20% between 2021 and 2022. They used 5 billion gallons in 2022 alone.
5 billion gallons.
And Microsoft's use went up 34% in the same period. These are huge numbers, but they become really concrete when you look at local impacts.
Like in Newton County, Georgia, that was a case study in the source material, wasn't it?
It was a really stark example. Meta built a huge data center there, and almost immediately, nearby residents who relied on private wells started having serious problems.
Yeah, the local reporting described people's taps running dry or the water coming out full of sediment. Wells they'd relied on for years suddenly became unusable.
And replacing a well is incredibly expensive for a homeowner. Meanwhile, the Meta facility is estimated to be using around 500,000 gallons of water per day.
500,000 gallons a day.
But it's not just that one facility. The systemic issue is that Newton County is already projected to face a water deficit by 2030. Residents are looking at potential rationing, and water rates are expected to jump by about 33%.
That's terrifying for the people living there. And yet, new data centers are still being proposed.
Oh, yeah. The reporting mentioned new applicants requesting permits for facilities needing up to 6 million or even 9 million gallons of water a day.
9 million, that's more than the entire county uses currently, isn't it?
That's what the sources suggest, yeah. It points to a fundamental disconnect in planning.
How do the tech companies justify this? Prioritizing cheap electricity over local water security seems hard to defend. Is it just about the jobs and tax revenue they bring?
That's the argument: jobs and taxes. But critics argue those benefits often don't cover the immense strain on local infrastructure, like water and the power grid. The core problem seems to be site selection criteria.
Meaning?
Companies often prioritize places with the cheapest, most abundant electricity. Water availability often seems to be a secondary concern, even if the location is already water-stressed, like, say, Phoenix, Arizona, or parts of Chile or Uruguay.
So they build in deserts or drought-prone areas because the power is cheap.
It appears that way sometimes, yeah. Water is treated almost like an externality, a cost someone else, often the local community, has to bear.
And this lack of foresight, this lack of maybe community consultation or impact assessment, links back to another big issue, doesn't it? The accountability gap.
Exactly. The water issue is partly visible because, well, you can see the impact on wells, but the energy consumption and the resulting carbon emissions, that's often much harder to track. It's kind of a black box.
Because the big AI companies, OpenAI, Google, Microsoft, they run closed models, right? They don't share all the details.
Precisely. Key operational data, like the exact size of the models, how many queries they handle, their precise energy use per query, the energy mix they use. A lot of that is guarded as proprietary, as a trade secret.
So researchers trying to figure out the true environmental costs have to essentially guess or reverse engineer the numbers.
Pretty much. They have to make estimates based on the open source models, like we discussed with Llama, or based on published papers, which might be out of date. It makes getting accurate real-time figures incredibly difficult.
And this secrecy matters hugely because of the type of power these data centers need.
Yes, they need power 247, 365 days a year, nonstop. You can't run these massive AI operations solely on intermittent renewables like solar and wind, not with current grid technology and storage.
So they need that constant, reliable baseload power, which
Often means fossil fuels. Natural gas, sometimes coal, depending on the region's grid. One study found the electricity used by data centers had a carbon intensity that was, on average, 48% higher than the U.S. grid average.
48% higher. So they're not just using a lot of power, they're often using dirtier power.
That's the implication. And data centers tend to cluster geographically, like in Virginia, which has the highest concentration in the U.S.
And Virginia's grid relies heavily on natural gas, doesn't it?
It does. Plus, you have the issue of backup power. When there are grid fluctuations or failures, data centers often rely on massive diesel generators to keep things running. That adds another layer of emissions.
It seems like a cycle of high demand met by often carbon-intensive energy. Are governments or regulators starting to push back on this lack of transparency?
There are signs of movement, yes. In the U.S., there's a proposed bill that would require federal agencies to assess the environmental impact of their own AI use. And the EU's AI Act includes requirements for developers of high-risk AI systems to report on energy and resource consumption.
So, some initial steps towards accountability.
Small steps, but important ones. Opening up that black box is crucial.
But in the meantime, who's paying for all the new infrastructure needed to meet this demand? The grid upgrades, the new power lines?
Well, that's another really contentious point. Research looking at utility agreements suggests that in some cases, the costs associated with building out the grid specifically for these massive data centers might actually be passed on to regular consumers.
Wait, so ordinary households could end up paying higher electricity bills to subsidize the power needs of these giant tech companies?
That's the concern. One analysis for Virginia suggested residents could potentially face an extra, $37.50 on their monthly bills just to cover these data center-related grid costs.
$37 extra per month to power facilities for some of the richest corporations on the planet. How is that justified?
That's the question utility regulators are grappling with right now.
Yeah.
It really challenges the narrative that these centers are purely economic windfalls for a region if the public has to subsidize the essential infrastructure they require.
Okay, it feels like we've painted a pretty concerning picture so far. Massive energy use, water scarcity, lack of transparency, costs potentially pushed onto consumers.
It is concerning, no doubt.
But the source material also pointed out that AI isn't just the problem, right? It can also be part of the solution.
Yes, absolutely. That's the paradox. AI is incredibly powerful at optimization, finding efficiencies. And sometimes those efficiencies can lead to huge environmental benefits that might even outweigh AI's own footprint.
Like the example with airplane contrails.
Exactly. Contrails, those white lines planes leave in the sky, they actually trap heat and contribute significantly to warming, surprisingly so.
I didn't realize they were that significant.
They are. And AI algorithms have been developed that can guide pilots to make very slight adjustments to their flight paths to avoid the atmospheric conditions where contrails form.
Okay.
One estimate suggested that if the entire aviation industry adopted this AI guidance, the reduction in warming effect, the CO2 equivalent saved, could be greater than all the emissions generated by global AI use back in 2020.
Wow. So one specific optimized AI application could potentially offset the entire sector's footprint at that time.
Potentially, yes. It shows the immense power of AI for positive environmental impact when it's applied strategically.
So the path forward involves harnessing that optimization power while simultaneously tackling the hardware and energy issues we've discussed. What are the main solutions being proposed?
Researchers point to a few key areas. First, making the models themselves more efficient. By focusing on developing smaller, more specialized models designed for specific tasks, rather than constantly pushing for ever larger general-purpose models that are often overkill for what users actually need. Tailoring the tool to the job, essentially.
Makes sense. Less wasted computation. What else?
Second is hardware innovation, moving beyond the current generation of GPUs. Things like neuromorphic chips.
Neuromorphic, what are those?
They're designed to mimic the way the human brain processes information very parallel. And crucially, they use energy mainly when they're actively processing data, not just sitting idle. That could offer huge energy savings.
Interesting.
And also things like optical processors, which use light instead of electricity to move data around.
Yeah.
Less resistance, less heat, potentially much lower energy use. These are longer-term hardware shifts.
Okay, so smarter models, better hardware. What about the grid problem, the reliance on dirty energy in places like Virginia?
That needs systemic change.
Yeah.
Obviously, transitioning data centers fully to renewable energy sources is key, but there are more ambitious ideas too, like distributing the computing tasks globally based on time zones, shifting demanding AI workloads to regions where renewable energy production, solar or wind, is peaking at that particular moment, sort of like following the sun and wind around the planet.
That sounds complex but clever. Using renewable energy where it's most abundant at any given time.
It's a big logistical challenge, but it tackles the intermittency problem head on.
Okay, so there are paths toward a more sustainable AI, but we can't wrap this up without touching on that classic economic concept, the Jevons paradox.
Ah, yes, the rebound effect.
Explain that. If we make AI way more energy efficient, doesn't that just solve the problem?
Not necessarily. The Jevons paradox basically states that when you make the use of a resource cheaper or more efficient, demand for that resource tends to go up, often increasing overall consumption in the long run.
So making AI cheaper and easier to run might just lead to us using it way more, potentially erasing the efficiency gains.
That's the risk. AI is often described as an accelerant for everything. Making it more efficient accelerates its adoption across the board for good applications, like the contrail example, but potentially also for more energy-intensive, maybe less critical uses. The total footprint could still grow.
That's a sobering thought. So efficiency alone isn't a silver bullet.
It's necessary, but probably not sufficient on its own.
This deep dive has really hammered home one thing for me. This AI revolution is driving energy and water demand at a pace and scale we maybe haven't seen since, I don't know, the Industrial Revolution or mass electrification.
It's a valid comparison, I think. The trajectory is incredibly steep.
And tackling it needs more than just individual users thinking twice about a query. It needs real transparency from the companies building these systems, and it needs smart, systemic regulation.
Exactly. The focus really needs to be on the system level, demanding accountability on energy sources, on water use, on model efficiency. Pinning it on individual consumption kind of misses the forest for the trees, given the scale and the secrecy involved.
Right. Which brings us to our final provocative thought for you, our listener, to chew on. We're moving pretty fast towards a future where AI isn't just answering questions, but acting as agents.
Autonomous agents performing complex tasks.
Exactly. Agents that might plan, research, generate multiple options, run simulations, tasks that are inherently sequential and much more computationally intensive than a single query is today. They'll require significantly more energy per job.
Yeah, the energy profile could shift again, dramatically.
So the question is, in that near future, with these powerful, energy-hungry AI agents becoming potentially ubiquitous, how do we policymakers, citizens, consumers, ensure that the environmental toll of all this amazing innovation doesn't just completely overwhelm our planet's finite resources, especially energy grids and fresh water supplies? How do we keep that acceleration in check?